Okay, so FRQ number 3, we have this rod that's falling down, pivot, and its pivot is right here at the end. And then for part A, it asks us to calculate the initial energy of the system. The initial energy of the system would be just PE, because it's not moving initially, so there's no KE. And then we know that PE is going to be mgh center of mass. It's going to be center of mass because since the rod is uniform, we have to use the center of mass because that's where gravity will be acting. And then our h center of mass will be, instead of the total height right here, it will be half the height. And then to find out half the height, I'm just thinking about drawing a triangle like this. H center of mass. We know that since it's half the height, we have to use half the hypotenuse. So it's L over 2, and we have our theta right here. So what's going to be is sine theta equals H center of mass L over 2. So that means our H center of mass would be equal to L over 2 sine theta, which would be equal to, when you plug it in, 0.866 meters. Okay, so now since we know the new H center of mass, we just plug in the numbers. Mass would be 4 kilograms, gravity 9.8 meters per second squared, and then H center of mass 0.866 meters, and then that would give you 33.998 joules. That. Oh, 948, sorry. Okay, next we have part B. It asks us to calculate the angular acceleration of the rod at instant it's released. So we know that it's net torque equals F moment of arm times R equals I alpha, like that. So now what we need to find out is F moment of arm. So F moment of arm is going to be the force acting perpendicular to the rod, so at the center of mass. So what I thought was, since F of G is gonna act down like this, the component that's gonna be perpendicular to the rod would be FGY. So that force pulling down like this is gonna cause the torque of the beam. So we know that FGY is mg cosine theta, right? So that's going to be our force that's going to be causing our torque. So mg cosine theta times r. R is going to be the distance away from the pivot, which is going to be L over 2, equals to the I value of a rod that's pivoted from the end. It's going to be 1/3 ml squared, and then just alpha like that. So I'm just going to plug in the values. It's going to be 4 kilograms times cosine times 9.8 meters per second squared, cosine 60, and then L over 2, which is going to be 2 meters over 2, like that, over, I'm going to multiply everything by 3 on the numerator, and then divide by mass, 4 kilograms, like that, and then divide by L squared, 2 meters squared, and that's going to give you your alpha. And then when you plug that into your calculator, you get 3.675 rads per second squared. Part C. It says that once the rod is released, as it rotates, does net torque stay constant, increase, or decrease? I say that net torque increases. This is because as the rod is falling down, so imagine the rod is falling down like this, until it's perfectly horizontal, So as it's falling down, the theta right here is going to decrease. So as falling down, theta decreases. But we know that the force acting on the beam that's causing our torque is mg cosine theta. So as decreases, cosine theta increases. Meaning that as the beam is falling down, since the theta is decreasing, that means mg cosine theta is increasing, meaning that torque increases as well. Part D asks us rank the following from greatest to smallest alphas from on points A, B, and C. So I say that alpha A equals alpha B equals alpha C. This is because all the alphas are constant, are the same on the rod. Because one part of the rod cannot accelerate faster than the other. That's like no matter the location. Like that. As you see, all of these, all the calculations for alpha, it doesn't depend on its location from the rod, because FGY is acting at the center of the rod anyway. Part E, it asks for, instead of alpha, it's asking for omega now. And I also say that omega is same throughout the beam, no matter what. This is because same alphas, meaning, so since all of the points on the beam have the same alpha, that means that all points pick up angular velocity at same rate. So all the omegas are going to be the same because all of the omegas are increasing at the same rate throughout the rod. Part F, it asks us to rank A tangential. So I'm saying A tangential C is greater than A tangential B greater than A tangential A. This is because A tangential we know is R alpha. And then since we all know that alpha is the same throughout, it's A tangential is dependent on R. And then since A tangential is dependent on R, the C is gonna have the greatest, since it's it has the greatest distance away from the pivot, followed by B and A. And then next it asks for AC now. So I'm gonna say AC C is greater than AC B greater than AC A. This is because AC is V squared over R. We know that V is R omega. And then when you substitute that in, that's going to give you R omega squared. Since we know that omega is same throughout, this is also dependent on R. Like that. So since it's also dependent on R, C has the greatest distance from the pivot, meaning that AC of point C is going to be the greatest, followed by B, and then followed by A. And then part H,